Hi guys, in this lesson I will deep dive into the concept of spans in NURBS geometry. We will explore what they are, what purpose they serve, and debunk some A-class misunderstandings regarding spans and their usage in professional modeling pipelines. But before I give you a definition of span, I need to introduce you to two very important parameters that NURBS geometry holds: vector knots and basis functions. They are essential to understanding spans, but rarely described and explained. In fact, you will not find much information about them in Alias documentation or A-class related articles. People just have no idea and make false claims along the way, which let's say impacts your decision making when using spans in your modeling. But you're among the lucky few, as we will cover these now. So let's start with the fact that a NURBS surface has a normalized parameter space, which means that it ranges from 0 to 1, representing an infinite amount, better say an infinite number of possible points in two directions, U and V. This means that a NURBS surface consists of a continuous two-dimensional domain of parameter values. So you're now looking at the surface just as an example. So this is a standard 3-degree surface with a single span. It has V direction. In this example, it goes vertical, and U direction, which goes horizontal. And the values between 0 and 1, we obviously don't see it here, but it's within the structure. And basically these two directions and the values with them gives us a grid of values, or a domain of values, better say. So as I said, it is continuous, which means that we know the beginning and the end. We know where it starts, we know where it ends, but it is continuous inside. So there can be infinite amount of points. And that's because this domain will be difficult to use, just because it is continuous. So to operate with it, it needs to be divided into known amount of segments, and that is exactly what vector knots do. They subdivide the continuous domain of parameter values into a defined number of segments called spans. So a span is an area of a surface divided by a vector knot. More subdivisions result in more spans. Fewer subdivisions results, in fewer spans. So this surface is a 1 span. This surface is still 3 by 3 degrees. It is 2 spans. This surface is 3 spans. So basically, they have more subdivisions. So each span is affected by certain CV due to the basis function. So not directly. A basis function is a mathematical function that defines the influence of a CV over a specific segment of a NURBS surface. So the vector knot defines the parameter space for the NURBS surface, and the basis functions are calculated based on these knot values, which means that spans are not containers for CVs, as some people claim. It's bullshit. They bound, yes, but not as a nested structure. So let me actually show you what these knot vector values actually are and how they affect the way how the multi-span surface behave. And for that, actually, let me go into the Photoshop, where I have pretty much the same surfaces as an Alias, so it's structural representation. So on the top we have 3 by 3 degree. Next we have 3 by 3 2 spans and 3 by 3 3 spans. So they literally just mimicking the same structure which Alias provides us in terms of the control vertices. So what is the vector knot I already described, but this is really important in my humble opinion, just to understand how these values are spread across the surface and how, just on the base level, they calculate. I will not be deep diving into the basis functions. I don't really understand them really well myself, and it's a little bit an overkill. But just, I believe that the knot vectors and the way how they visualize and represents is important to understanding of spans. So for the, we will calculate the knot values for all three surfaces. So let's start from the beginning, from the first one. So this is 3-degree one-span surface, and the formula to calculating the knot vector is actually very simple. Amount of degrees plus 1 multiplied by 2. So if you plug the values, 3 degrees plus 1 multiplied by 2 equals 8. What this number 8 means? Well, it means how many values, what kind of amount of values we will have in our vector knot. So we have two vector knots for every surface, one for a u direction and another one for v direction. They are identical, but you need both to form a grid, as I mentioned a minute ago. So it is a grid of values, and in line it will look like this. So for the surface 3-degree single span, it will look like 0, 0, 0, 0, 1, 1, 1, 1. And actually, if I will show it on the grid, just quickly represent it, it will look somewhat like this. So that's very important here that we have a repetitive value. So we have 4 zeros and we have 4 ones. And if you notice, you will realize that the amount of vector knot values is equal the amount of control vertices. But that is true only for a single span surface, when we have only one span. So we have a surface, it already consists of span, obviously. So in the other examples, so when we have a multi-span surface, we have a different formula, slightly different formula, and we have a different amount of vector knot values. Just to visualize it, now I understand what it actually means. So this is the 3-degree two-span surface. And as you see, there is a slightly different formula. So the number of knots will be equal of 2 times of degree plus 1 plus span minus 1. So if you plug the values, you will get the value of 9. We don't have 9 control vertices in the grid, isn't it? So if we look at the linear structure which consists within the vector knot, you will realize that it's a little bit different. So we have 9 values, but now as we have a span, we have not 2 different values, we have 3 different values. We have 0, we have 1 in the middle, which is 0.5, and we have 1s. So now there is a 3 groups. So if I will open up the third example, and you will notice that this one, do I have it actually? Yeah, I do. So it has the same formula. For multi-spans, we have the same formula, and it will have already 10 values, right? And our structure will look like this. So now we have one group of parameters, second group of parameters, third group of parameters, and fourth group of parameters. And these points in the middle, 0.33, 0.66, they are marking spans. Same here, or the beginning and the end of a segment. Same here, 0.5 marks the middle. Actually, let me visualize. So the 0.5 marks the middle, and in this example, it will be these two, so 0.33 and 0.66. So we have group number 1, group number 2, group number 3, and group number 4. They are control vertices which are within the different segments. So on top of that, I would like to mention that there is a visual difference in terms of how CVs actually spread out. So this one is very uniform, but this one is already not. And this one is even worse. Why was that? I will answer it a bit, but let me actually tell you what these repetitive values actually mean. So every repetitive value in the knot vector shows a separate segment. I believe you already figured it out. And a value used for a basis function for control vertice. And this is very important because these values will be plugged to the basis function. just as we already discussed, in a single span surface, all of the values, so here's the single span, so all of the values in the grid will be uniform, right? Thus, every single one will contribute to the whole surface. Every single CV will contribute to the surface. In contrast, in example number 2, in this one and this one, we see more than one segment with different values. And that means that when plugged into the basis function, I mean its values will plugged into the basis functions, they result in a situation where CVs contribute to a specific part of the surface instead of affecting all of it. So they contribute only to a segment. They doesn't have contribution to the whole surface in general. So once again, in example 1, all CVs contribute to the whole surface. In example 2 and 3, spans split CV zone of control. There are no CVs that contribute to the whole, only to the dedicated part. So, and an important nuance is the non-uniform distribution of CVs. As I said, in multi-span surfaces, so you can see they're definitely not uniform. It happens because it happens because of the structure of the knot vector, which introduces a localized control points at span boundaries, enhancing the ability to control the shape and leading to the observed non-uniform spacing. This is important as well because there is, as I said, localized control points at span boundaries. That means that we visually, in the multi-span surface, we see less control vertices than actually are or actually supposed to be. And that's because now they actually exist. So the underlying structure, they actually exist, but visually they not. They kind of merge together at the boundary. I'm saying it merge like casually, they not technically merge, but you don't see them. They operate as a single control vertice, and it's not treated like a CV multiplicity, by the way. No. They really will be treated as a single control vertice by the interface of Alias, but underneath they're not. So it designed to maintain continuity between the segments within a single surface. And that's why there is less amount of control vertices in comparison to the amount of the vector knot values. So that's because we are not see all of them. Where was I? Spans are not inherently good or bad. They are fundamental to NURBS geometry. You cannot make a NURBS surface without a span. The question should be about the number of spans for your surfaces. Should you have more spans or fewer spans? And the answer to this, is very simple. It depends on the surface. The more complex the surface should be, bending and rotating a lot and kind of aggressively, right? The more fidelity or, say, resolution it should have. But there is a limit and a catch. In Alias, we can't make more than 9 degrees for the single span surface. In fact, let me actually illustrate it. So here in Alias, I will try to bump it up to more than 9 degrees. And I can't. So it's just impossible. I believe that in Rhino, if I remember right, correct me if I'm wrong, it is a 7, not 9. And in every specific surface modeling tool or CAD modeling tool, the number is different. But it never huge. Why? Well, because more complex polynomials become unstable, difficult to compute in real time, and carry more possible errors. So we split the surfaces into chunks, segments, with CVs that contribute only to a specific portion of the surface, which I said before, and bumping the complexity and ability to morph the surface, let's say, beyond its base limit. Of course, that's it's not all unicorns and rainbows, and increasing complexity through segmentation by adding more spans may lead to imperfections and bumps on the surface. So I mentioned it a few times before, and I will say it again. We are not perfect, and our tools are not perfect either. That's why NURBS modeling tools give you an option to choose an experiment. So basically kind of see what works better in specific situation. And in practice, community based on, let's say, collective experience defined a simplified rule how to operate with the spans. And actually for that, let me open up another example here. Okay, so in front of you, you're going to see pretty much the same example, different type of fillet structure and a couple of planes. So let me actually voice the rule, and then I will show you how it actually applied to the practical examples. So the rule stands as follows. If one span surface doesn't have enough complexity to deform the way you want, add more segments, spans, and to eliminate possible errors in surface quality that spans may produce, split it into separate surfaces by dividing the surface at their segments using an alternative calculation method, Bezier. We have a checkbox Bezier within multiple tools in Alias. I will show you one in Fillet tool, and a standalone instrument for that, and I will show it as well. So basically what it does, it converts a multi-span NURBS surface into a collection of single span surfaces, also known as Bezier surfaces. In general, it works as follows, just very quickly. The multi-span surface, divide it into segments at each knot value, right? Creating an individual surface for each span. Here is a very simple example. Here, there is a multi-span surface, right? And this is a single span surface stacked together. So that is the process. I will show you in a bit how it's done. Now, each of these segments is converted into Bezier, which means that now defined by a single polynomial. So every single one of them is a single polynomial. But you should be warned that manual adjustment may be necessary to ensure seamless transitions between these newly created Bezier surfaces, so continuity in this situation may break. And it may not. It depends on the complexity and luck, but basically this is the kind of fundamental universal approach for the professional industry. So when you're modeling it professionally, this is in most situations the way how you will approach the problem with spans. Now let me actually illustrate it on these three bricks. Now as you can see, they have a kind of wobbly surface from the top, right? Which means that the edge will be quite complex. And I decided to illustrate this example, or this rule, on a fillet tool, but it's not necessarily it can work with any other tool. It's not really that important. What's important here that I can show for the fillet tool, which is extremely powerful, all the variants which defines the spans of today's topic. So in this example, let me actually activate the history. You're going to see that I made a fillet, basically a transitional surface between the two parts of the model, and I build it using one surface. So all of these ones, so this one is a one surface. It is a continuous surface. Oh, it has a beginning and end, obviously, so it kind of bites its tail, and all of these lines are spans. So if you look at the control panel, you're going to see that I have 5 by 5 degree surface, and I have 144 spans. Now, it's beyond the limit I actually safely can do in my construction tolerance set, so this variant definitely not work for me. But as you can see, that Alias managed to do exactly what I described before. So separated, bring vector node values, then separated using spans, and bring different influence of control for the control vertices. And it actually gives you an ability to do really complex transition, because this fillet is a chordal one, so its length is actually constantly changing. So this is a quite a heavy calculation, and the polynomial for this is crazy, and the structure for that is quite complex. But as you can see, Alias can handle it pretty fine. And not only Alias, most of the CAD systems are really good at this. You know, the Rhino, you know, like Fusion 360, whatever, they all do it pretty much the same way. But there is a catch, though, of course. Now, first of all, it's pretty complex. There is a lot of spans, and the continuity is not guaranteed. We have too many spans. In fact, if I will check it, you're going to see that I'm even locking position. And I'm locking position because I have a very tight tolerances, but that shows, right? Let me check it here. Yeah, we have a problem in continuity. Let me check it here. We have curvature issue on this side, right? But this is basically the single span surface. Now let's go to this example. In this example, it's slightly different. So for this construction, the single span surface was created in the beginning with all its domains, and then it's separated by chunks based on a basis function, and basically separates on few different surfaces. So as you can see in the surface structure, it's set to multiple surfaces. So I deliberately switched it to multiple surfaces. So now this surface and this surface and this surface are separate, right? But within the surface, the spans are still happening. So Alias has an ability to add more definition through the spans if there is not enough fidelity for the surface to bend the way it's supposed to be, right? So this is kind of the middle ground between these two examples. The unwanted result, wanted result, this is something in between. And the problem here is that it definitely maintains the curvature better. At least there is no positional error anymore, which is great. But sometimes we still have some issues. On top of that, I would like to mention, I forgot, that when you have a span, it is obviously a single surface. So the connection between them, you can't even check for curvature. It is curvature. It's designed the way that it's supposed to be. Same here. Within the span surface, I can't really check the curvature. It is already curvature within it. But the edges may fail, as I said in the description of the rule. Now let's go to the last example, this one. As you can see, this is very complex, a lot of spans. There is less amount of spans, and this one has no spans at all. Kinda no spans at all. So if I will pick the surface, you're going to see this is the separate pieces. All of them are separate pieces. And in fact, their structure is much simpler, and there is less amount of segments, and the continuity, well, kind of the same, to be honest, with the previous one, but it's much easier to operate with that and realign. Let me actually turn off the comps to see how big the deviation is. No, that's manageable. That's manageable. Yeah. So, let me check this one. Yeah, so we have pretty much the same result in the previous one, but the structure itself is much simpler. We have more amount of the separate surfaces, but it's much easier to realign at the end. So this result, let me just activate the history. You're going to see this is a multiple surface, and this is the checkbox, Bezier surfaces. So the process, let me just repeat the steps. So it's very simple. It actually creates the same structure. So a single span, a single surface, multi-span surface, and then for the base functions, it's separated at the vector using the segments. So it separates it through the segments pretty smartly. So it's not just like you just take it as it is and then just separate it on million parts. You're going to see that the structure is quite different, but the original surface for this result will be this surface. and just calculate it using the basis function quite heavily. So as you can see, these one, for example, they're not matching. I can't cut it here, but in this example and in this example too, in this one and in this one, they actually in line here, and I believe, oops, zoom out, and here. Now, it's not ideal, right? It's not ideal. It's not following the proper flow, but it's manageable. We can fix that. So originally this surface, which is technically a single span surfaces, where, you know, people in A class will say, yeah, this is the proper way of doing that. They actually, the process, the algorithmic process of converting this to this. So in fact, this is, that was spans, but we separated using this algorithm. So you can say that, yeah, I'm working with the single span surfaces. That's technically true, but the original is a multi-span surface anyway. And let me be clear here, without this underlying structure, which then converted to something like that, manually having the coral fillets here, it will be really difficult to build manually. So you need a solid structure which you can tweak further, because none of these examples are actually A-class. They all have errors. With my tolerances, they have errors, which means that they're not suffice. And in fact, I see a lot of stuff like this one is a no-go. The flow is wrong. So I will rebuild that if I really need a finalized result. But this is a good foundation. I can build on that further. So I can realign, extend, cut, rebuild the curve, delete a couple surfaces, extend these ones, and yada yada. And actually made it in a few modeling videos before. One of them is bolt nut cap. Check it out. It's just one of the few videos on this channel where I actually methodically do all of these A-class passes. But overall, it is a good basis. So spans are not a bad thing. They are actually essential for you to model, and eventually, if you want, you can get rid of them. So, and as I said, there is not only the Bezier checkbox in the surface structure for the tool, for surface fillet and for any other tool, but there is a specific instrument for that. So, for example, here you're going to see I have a surface. This surface has randomly placed 5 spans. I did it manually, basically inserted the spans. And these ones are separate. And I did it through this specific tool called NURBS to Bezier, this one. So you select your surface, you know, you click on this stuff and just split, and now we have the separate parts appear. Here they are. So it does exactly what I described before. It separates the surfaces at the edges of a segment, so at the vector nodes, which marks the segments. Now, both of these approaches, so using Bezier surfaces that splits it automatically, using the NURBS to Bezier, which manually separates based on the vector nodes, they both are good and kind of like a standard approaches for professional modeling. You rarely end up with a result like this and call it a day. Even though, once again, I'm saying multiple times, I said it again, the spans are not a bad thing, it's just too much. Now, this one is much better. I have time, then I will convert it to something like this. I have time, I will tweak this and make it better. And this is actually the process of getting to the really, really high quality models. So let me actually focus on the A-class a little bit. So as for A-class, spans in general are an option up to some manageable limit. So not like this, definitely not like this. Now, generally, no more than 10 spans are recommended. And once again, it really depends on the industry and depends on the studio. There is no one universal rule. Because, you know, sometimes 100 spans can produce you a good surface, but it may lead to issues in production. So your engineering department will warn you in advance how many spans they can carry, and maybe you can carry none, and then you convert everything to the separate parts, right? But yes, spans may be a part of A-class, and in most cases they exist in their natural form, well, like this, or in its split form, like this, as a Bezier surface I mentioned just a few minutes ago. So, guys, as a conclusion, spans are a fundamental aspect of NURBS geometry, and their proper use can significantly impact the quality of your models. They enable a complex assemblies, enable to construct a complex assemblies. Once again, look at this one. Try making this yourself. You'll spend a lot of time. It's much better to have an underlying structure to be converted to something like that, right? So it really can do a complex assemblies, especially when we're talking fillets. Fillets is just multi-span fillets are actually just perfect. Not perfect, but acceptable. But of course, sometimes these spans can cause surface issues. So you pay attention to these details, and if errors occur or the structure is too complex, use the Bezier split. So basically the way how we split the surfaces, or how I split these surfaces using the Bezier checkbox. This gives you a benefit basically of both a single span simplicity and at the same time complex assembly. So the benefits from spans from the single surfaces at the same time. However, check your edges for continuity, as it is not guaranteed. It is not a single surface, which means you may have issues and you need to address them. You need to realign that manually. All right, guys, that's pretty much all what you need to know about the spans. I put some heavy theory into that, but I truly believe that it's better to know a little bit more than just like, oh, this is a checkbox and, push the checkbox, right? Knowledge is power. Anyway, thank you very much for watching, and I will see you in the next one.